In the last video, we were talking about stable nuclei. Well, what if you have an unstable nuclei? Then it will tend to decay and form particles that are stable. That's called radioactivity. It's a process by which a nucleus emits one or more particles, or it could be energy, in hopes of becoming more stable. Now, there are different methods, there are different options for an unstable nucleus to decay into something more stable, and the one we'll look at now is called alpha decay. So this is an option if a nucleus is unstable because it has too many neutrons. We could release what's called an alpha particle to become more stable. We mentioned alpha particles when we were talking about the gold foil experiment. Rutherford had a source of alpha particles, and they were these little positive particles. Basically, an alpha particle is just a helium nucleus. Now, it's not a helium atom. It's a helium nucleus, which is why it is a positively charged particle. There are no electrons. Here is the symbol, then, for the alpha particle, or the helium nucleus. And we kind of remember then from the last chapter. Here's one way of writing nuclear symbols. This on top is the mass, and then on bottom is my atomic number. Atomic number. So this helium nucleus has 2 positive protons and 2 neutral neutrons for a mass that adds up to 4. So in this little picture here, here's my alpha particle. I don't know, we could pretend that these blue ones are the protons, positive proton, and there's one more in the back there, positive proton. And the red ones are my neutral neutrons. Something kind of like that. This is my symbol for proton, by the way. And this is my symbol for neutron. Little protons that are positive, little neutrons are neutral. They have no charge. So overall, the alpha particle is a positively charged particle because there are no electrons. Alright, so here's what happens. We have a couple options here. Visually, I have this americium atom. And remember, the other way that we could show nuclear symbols is by putting either the element symbol, or it could just be the name written out. And then at the end, this is the mass. Americium, with a mass of 241. Which I could look up americium on the periodic table. And I could also write the symbol like this. Am. The mass is 241. Americium is number 95. This americium atom is unstable. So in hopes of becoming more stable, we're going to remove an alpha particle from the nucleus. We're going to remove a particle equivalent to 2 protons and 2 neutrons. And now watch what happens. We form some neptunium, which could also be written like this. Mass 237, neptunium, number 93, plus this little alpha particle, a helium nucleus, or 2. Nuclear reactions are really not difficult. Look at this, it makes sense. All particles must be conserved in some way. In this type of reaction, this alpha decay, I'm not destroying any protons or neutrons. They are all accounted for on both sides. So americium started with 95 protons. It decays into a particle with 93 protons, and then we release the alpha particle, which was the other 2 protons. So the number of protons adds up to 95 on both sides. Here's 93, and then 2 more from my helium nucleus. 93, 94, 95. All of the protons are accounted for. We've just split that giant americium atom into 2 smaller particles. I would assume then that the neptunium must be more stable. And now we don't know. I mean, this could further decompose or further decay. I mean, the neptunium could let off another helium nucleus. And this would keep going until we finally reach a nucleus that is stable. So this might just be the first of many alpha decays. The other one that they give me as an example up on top, here's an atom of uranium. Mass 238, atomic number 92. If I lose a helium nucleus, or an alpha particle, the number of protons will go down by 2. So I form element 90. If I look at the periodic table, element 90 is thorium. The mass will go down by 4. So the mass went from 238 down to 234. And then again, we release that helium nucleus, that alpha particle. Now we'll kind of describe some alpha decay down at the bottom. This is, I don't know, one of the more docile forms of radioactive decay. It can be blocked by a thin sheet of paper. It does not penetrate directly into your skin, although you would not want to be around a radioactive source for long, because if you do inhale alpha decay or ingest it, then it could cause damage to your internal tissues. Some of these we'll also talk about in class, like what are common sources of alpha decay, and like what might be some of the side effects if you are exposed to it. Some sample problems, some practice problems. Alpha decay. I have my original nucleus, it must not be stable. I know it's alpha decay because I see that helium nucleus. The helium nucleus will always be the indicator of the alpha particle. Alright, so we just have to find the missing product. Okay, so again, all particles must be conserved. We're not destroying any protons or neutrons. So if I have element 88 radium, and it emits a particle with 2 protons, the atomic number will go down by 2. I usually like to do that first. The atomic number will go from 88 down to 86. Then I look at my periodic table to find what is element number 86. It's radon. Then I can put the symbol in. This is radon, element 86. Now again, there are many different isotopes of radon that could exist. This particular isotope would have a mass of 218 because 218 plus 4 should equal 222. So you take the original mass, drop it down by 4. Now I get it that if you do look at a periodic table, that might not be the mass of radon. This is just the particular isotope of radon that would form in this particular decay. Now maybe that's not stable. We could undergo more and more alpha decay until we do hit a stable nucleus. Alright, let's try one more. How about some polonium? Okay, so I like to do the atomic number first. It's going to go from 84 down by 2 to element 82. So I look on my periodic table, element 82 is lead, Pb. The mass number should go down by 4, so this would be 204. One particular isotope of lead. And again, it might not be the most stable, I get it. On the periodic table, lead's mass is a little bit higher than 207. So if this lead atom is not stable, we could undergo successive alpha decays until I do hit something that's stable. So there's a good example of how to fill in these nuclear reactions from alpha decay. The atomic number will go down by 2. the atomic mass will go down by 4. So that if you add the two atomic numbers and the atomic mass is on the product side, it should equal the original mass and atomic number on the reactant side.